Hello and welcome to Engineering Physics 3BA3. 3BA3, we're going to use a great electronics book. This is one that uses a physical approach. It's by Snoke. I really like this book. I hope that you will too. What these lectures are going to be is a guide through the lecture notes that you'll find online, so you can get all of the text for this online. If you prefer to just read and not hear me talk over the lecture notes, then that's fine too. You can do that. You're free to do that. This is going to be hopefully something that'll just help you if you like to be more of a audio learner. So EngPhys 3BA3 has digital and analog electronics in one course, similar to 2EO4. 2EO4 also does that. Second term, if you're continuing on with this course this year, we're going to be spending a lot more time on microcontrollers, but the information that you need in this course is very valuable for you, that microcontroller stuff. So this is kind of the fundamentals, the regular circuit stuff. Next term, it's mostly a project course, and even more useful is this is going to help you get to the fourth year design project course 4A06 with a lot of background information that's quite useful. Probably more than any other course, 3BA3 and 3BB3 prepare you for 4A06. Okay, so a lot of the topics in this course you've seen before. This time we're going for mastery. So we're going to start on some introductory stuff that you've already seen, but this time try and learn it better. If you've seen it before, learn it better this time. If you already know it, then skip through to the next part of the lectures when this stuff comes up. Up to you. Why do you need the textbook if you have these notes? These notes use a lot of slides from the textbook. It's not a complete replacement for what's going on in the textbook. Instead, you're going to use this as kind of an introduction to and a check on whether you've understood all of the sections. Definitely go back to the textbook. I recommend that you read that if you're not sure about something that we've talked about here. Okay, getting right into the material, linear DC circuits. Chapter 1 is going to be very fast because this is mostly review material. Circuit elements, the water analogy. So electrical current is kind of like water current, and voltage is like a pressure difference between one point in a pipe and another, in that voltage is what causes current to flow, and there's always some resistance in a electrical circuit, just like in a water pipe, unless we get into superconductors, but let's ignore that for now. The current through a resistor is proportional to the voltage drop across it in that equation of Ohm's Law, in that we can write Ohm's Law, I12 is V1 minus V2 over R. I12 is the current from point 1 to point 2, and V1 minus V2 would be the voltage difference across the resistor R, the voltage drop across the resistor R. Now, resistors are used to impede current while maintaining a voltage drop. So a water-saving shower head maintains a water pressure while restricting the water flow. A short is a negligible resistance between 2 points. An open is an infinite one. A ground is some location that we've called potential 0 volts. You may remember that just like potential energy, electric potential only is a relative term. So it doesn't make sense to talk about the potential at some point unless you've established a reference point that you're going to call 0. In first year physics, you'd usually use 0 volts is some point infinitely far away. In circuits, typically 0 volts is somewhere in the circuit, so that you can refer to other points in the circuit relative to that and not have really odd or large voltage numbers. Wires in a circuit are often considered as having 0 resistance, and consequently have to have 0 voltage drop across them, but they could still have some current going through them. Really, that's an approximation. Wires will have some resistance. And another thing to consider in a real circuit is contact resistance. Whenever you have a metal connected to another one, there's some resistance required to jump across that surface. So this contact resistance and wire resistance, depending on the circuit that you've got, it's typically on the order of 1, 2, or 3 ohms. So if you want to be able to ignore all of the wires and all the contact resistance, it's usually a good idea to build your resistors in the circuit to be on the order of kilo ohms or maybe tens or possibly hundreds of kilo ohms. Then you could say that all the resistance is just from your resistors and analyze it the way you'd like to. Current across and voltage through a circuit don't make sense. Just like height, you wouldn't ever say the height through this ladder. So it's the height difference from one point in the ladder to another point that would help you calculate potential energy. And so you wouldn't say the voltage through something. Similarly, you wouldn't say the current across a circuit element. It's current through the circuit element. Right. Okay. Ohm's Law and power. Ohm's Law is a familiar relation that V is IR, which you learn in first year, probably even in high school. It's basically the state equation for a resistor. It expresses the idea that a resistor is an element that linearly relates the current through it to the voltage across it, where the relation between them is a constant called the resistance. One way that you can actually derive Ohm's law is to use linear response theory. Now, this is going to be a very hand-wavy definition, if you can even call it a definition. All this says is that, well, anything, as long as current is just a function of voltage, then you could write it as a Taylor series. And should there be a constant term? Well, no, because if there's no driving force to make current flow, then there shouldn't be any current. So without a voltage, then there's no current. Okay, so no constant term. You see we changed the sum from n equals 0 to n equals 1. Then we're going to drop the power 2 in higher terms as long as delta V is small enough and we've got a linear response. That's all there is to it. Now this is not something that you can say will hold up for a very large amount of space, and obviously it depends on how big the constants are, where this is a good approximation or not. But it's one way to get started on saying as long as your perturbations are small enough, you can say anything goes like a linear function. That's going to be not as good around the bottom of an energy well where the linear term can vanish as well, but we don't have a good argument for why the linear term should vanish for resistors, so we're okay with this linear relationship. Another derivation for Ohm's law, which is going to be a little bit more rigorous than the last one, comes from viewing electrons in a conductor as classical gas molecules, which is to say that they primarily scatter off impurities in the lattice, so they're kind of bouncing around in there like the molecules of a gas, and we're going to look at how they would behave in that. This is kind of a weird picture of electrons and really ignores everything that's going on in quantum mechanics. But interestingly, if you use this derivation, you can come up with some reasonably accurate answers in terms of resistance and resistivity. Okay, so let's see how this goes. After each collision, the electron's velocity is randomized. So you imagine that the electron smashes off some impurity in the lattice, and then it gets a random velocity. So it could be going forward or backwards, it probably has some average speed, but the velocity itself is randomized. After that, though, it starts to accelerate due to the electric field. So the electric field that's in the conduction medium because of the voltage that we're applying. Now, the average time between electrons between electron collisions with this lattice, we're going to call 2 tau. 2 tau is the average time between collisions. So then the hardest part in following through this derivation in the book is to think about what is the average time an electron has gone since its last collision. So if you were to pick an electron at random from in the metal, some conduction electron, just pick it at random, then say, okay, how long has this one gone since its last collision? How long has this one gone? If the average time between collisions is 2 tau, the average time each electron has traveled since its last collision, when you just look at them at random, not during a collision, but just look at them at random whenever they're flying around, would be just 1 tau. Okay, so the average time an electron has gone since its last collision is 1 tau, which means you can get that the average speed, the speed halfway between collisions, would be a times tau, so proportional to tau, where a is the acceleration force over mass. The force is the charge times the electric field, and you know the electric field is the spatial derivative of the electric potential. So that's the force on the electron. M, you know, electron mass. Q, electron charge. E, electric field in the conductor of length L, given by the voltage across it. Okay, so just recapping here, the average speed an electron in the medium is going, given by electric charge, average time an electron has gone since its last collision, divided by its mass, divided by the length of the conductor, multiplied by the potential difference across it. The currents, the rate of charge flow, so like what current means is how much charge is flowing through per unit time, flowing through a given cross-section. So if n is the electron density, electrons per unit volume, and a is the cross-sectional area, then we'd multiply those two together times the charge of each electron times the speed that they're going to figure out what the current should be. This kind of gives you volume units here. So if you take A multiplied by V, it's like a volume per second. So multiplying that by the number per unit volume and the charge per number would explain why this is the current. All right, so substituting the average velocity that we got into this current equation, we can come up with this relation. And now why don't we just call this constant in front 1 over rho, and then why don't we call this collection of constants here 1 over r, thinking that, oh, well, that's the r that we got earlier. I is proportional to delta v. We've derived that. The thing in front is just a constant. So this derivation also gave us what r is in terms of some material parameters. So basically this tells you that the resistance of a resistor depends on some material property called the resistivity. The length of the resistor, the longer that is, the more resistance it is, divided by the area. If it's got a bigger cross-sectional area, then we'd have lower resistance. That kind of matches your model for resistance. And how does the resistivity of a conductor depend on things? Well, the resistivity increases with mass. It decreases with electronic charge squared. Density of the electrons that are used for conduction, so the conduction electrons, it decreases with increased time between collisions. So if you have a more perfect lattice or more conduction electrons available, other things equal, or imagine that you had you had some magical material where the conductors, where the charge carrying bodies weren't electrons, but were something that had a higher charge, then those things would increase the conductivity, the inverse of the resistivity. Now we can give a name to this, to the material dependent properties here as well, commonly used, called the mobility. So the mobility is something we'll see a little bit later as well, and that you'll see in applications of quantum mechanics. If you take 3FO3 in engineering physics, mobility is a good parameter to talk about because it removes the conductivity's dependence on electron density. So you can talk about how easy it is to transport through this crystal, and that kind of scales and depends on different things than the actual number of charge carriers that are available per unit volume n, especially for a semiconductor. Another useful property of this derivation is that we can, even though it used some assumptions which aren't that justified at the start, we can get a lot of mileage out of this one and even figure out what the power loss is for conductivity. So power loss is given by the energy loss per collision times the rate of collisions, right? The energy loss per collision, we said that the velocity is randomized, so they basically lose their kinetic energy. Now, why did we put in 2 v bar here? Well, you remember that the time between collisions was 2 tau. The average time an electron has gone, though, is just regular tau, and that's where we got the average velocity of electrons. So when they collide with each other, then they're going twice as fast because they've had twice as long to accelerate for the same acceleration. All right, so the rate of collisions would be the density times the volume, because that's just the number of electrons inside the resistor total, number per unit volume multiplied by the volume, divided by the time between collisions. So number of collisions over a unit time. Okay, multiplying this out and substituting in what we had earlier, we find that the power loss is delta V squared over R. If we substitute in the current, then we can write this in a couple of different ways. Power is I delta V, is I squared R, all useful things to know, and ones that you probably already knew from first year. All right, 1.3, the voltage divider, concept of circuit inputs and outputs. A voltage divider is a shortcut to finding the voltage across one resistor of 2 placed in series if you know the total voltage across both. So here's an example. You've got these 2 resistors. They are in series because all the current that goes through one goes through the other. That's what series means. Very good to know that. Now, why is that true? Because this is a voltage meter, a voltmeter, and no current goes through that. So you can pretend that's not even there. Just don't worry about this little guy. All the current that comes out through there goes through these 2 resistors. Okay, so that means the two resistors form a voltage divider in that they divide the total voltage drop provided by this battery between them. How much does each resistor get? Well, the bigger resistor gets more voltage according to R1 over R1 plus R2. If R1's bigger, it'll be a bigger share of it. If R2 is bigger, then it'll get a bigger share of the total voltage. This isn't anything new, right? Like you could just get this from Ohm's Law. It's more like a corollary, but it's a useful shortcut to know. Why is that? Well, it's like you could say that, the word shortcut is kind of a combination of a bunch of different letters, and maybe at a higher level, it's a combination of letter sounds. But if you want to be able to read fast, it's better to know entire words so that you can just look at larger chunks of knowledge. In fact, you may look at sentence structures as kind of another higher level of that. So as we get to third year circuits, as we're getting better and better at this, then you want to not have to do your Kirchhoffs laws every time to figure out what the voltage that R1 gets. There's such a common circuit element that it's good to just know the voltage divider and know the result right away. It'll help in your design if you can get to this level of abstraction. Let's talk about some reality for a second. I know how much we hate doing that, but let's talk about reality. We often assume that a voltage source and detector are ideal, but really every voltage source has some internal resistance in series with the source, and every detector must allow some current through in order to detect the voltage, so that a real source and real detector form a voltage divider. So here's the ideal case. We like to draw this out. You put your voltmeter across a voltage source, and what do you measure? You measure the voltage that it's putting out, right? Well, maybe in actuality, there's some resistance for the source, and there's some resistance in series, or in parallel rather, with the detector. It's got to let some current through for it to be able to measure anything. So in reality, there's a voltage divider formed whenever you try and measure the voltage output by a source. Sources in a lab will usually tell you how much their output impedance is, so that you can do things like match the input impedance so that you get exactly the voltage that it's listing when you do maximum power transfer. This can be kind of confusing to new lab students. If you've got a function generator that says that it's putting out 10 volts peak to peak, but has an output impedance listed as 50 ohms, then oftentimes it's actually putting out, it has an output impedance of 50 ohms, and it's actually putting out twice as much. It's putting out 20 volts peak to peak. What it means is that it would be 10 volts if you were to put it across something with an input impedance of 50 ohms as well. Kirchhoffs Laws. Kirchhoffs Laws give us a systematic approach for solving more complicated circuits. You guys know these. Kirchhoffs current law, the net current flowing into or out of any node must be zero. What's a node? It's some spot where there is more than one way the current could go. So something like this is a node, something like this is a node. Kirchhoffs voltage law says the sum of all the voltage drops around any loop, any closed path you could go from one spot to another, has to add up to zero. So you could say the voltage here, voltage change there, and then back to the start must add up to zero. These laws and the current voltage relation for each element give you enough equations to solve for all the unknown voltages and currents. Now, how do you actually do this? So first thing you do is you assign the currents to all of the different branch elements, and then you figure out which side of them is going to be positive given what direction you picked for the current. Then what you do is apply the loop equation for each independent loop and apply the node equation for each independent node. Now, how many equations do you get? Well, you can do a node equation here, but then this is going to give you the same information. So you have the number of nodes you have minus 1. How many loop equations can you do? You can do the number of interior loops. So this loop and this loop. If you want to do an exterior loop, you can get a little bit more complicated. So in this case, we have one exterior loop. It turns out that that's redundant with the two interior loops. You could add this equation and this equation together and get the same equation as this. So you have a little bit of option. Sometimes it's more convenient to do an exterior loop if there's only one specific thing that you're solving for. If you need to solve for everything, then you're probably better off just not overcomplicating it. All right, let's see if we can recap that. Assign the current directions, write the positive side on the passive elements, traverse the loops writing the equations, write the equations for the nodes. You can do the node equations first if you like. So if you know how to do that, then pause the video and do that yourself. Okay, everybody back. Let's see how you did. So here's the current directions assigned. You could have yours going in an opposite direction. You could have them labeled differently. That's fine. The key part is that you put a plus sign on the part of each resistor that the current for that branch is going in. So the current goes in the positive side, out the more negative side of each resistor. It has to, because current flows from higher to lower potential in a resistor. Now, what kind of loop equations do you get for this? You can write the loop equations in whatever direction you like. It's good to be consistent about how you traverse the circuit. Personally, I like to always traverse in a in a clockwise direction and start at the bottom left corner of each loop for some reason. You can do whatever you like. That's how I like to do it. It's good to be consistent so you don't get confused. So starting at the bottom left, we'll traverse in a clockwise direction, adding up the voltage rises, subtracting the drops to get all of our equations. Go ahead and pause the video, try that out. Welcome back. All right, here we go. Loop equations. Bottom left loop, we go up by V1, down by I1 R2, down by I3 R1, and we're back to start. Loop 2, up by R1 I3, down by R3 I2, down by V2, down by I2 R4. Now the one node equation at the top, you can see we got I1 going in, I2 and I3 going out. And that's it. Several resistors in series have equivalent resistance of their sum, so you can add them up if they're in series. If they're in parallel, you know it adds like the inverse of their inverses. So 1 over the resistance in parallel is the sum of the inverse resistances. This is because 1 over the resistance you can think of as the conductance, and if you've got more paths in parallel, then the conductances add together. All right, first set of practice problems 1.2. Usually the practice problems will show up at the end of the lecture. Lecture 1 is kind of a combined one. It's about twice as long as a lot of the other lectures that we're going to have. So this is because we're doing review material and you can probably skip over a lot of it. So it's twice as long, but it's easier stuff. I guess that's a bit of a trade-off there. Now, let's do this question. So what do we got here? This is exercise 1.19 from the Snoke textbook. In the voltage divider shown in figure 1.9, this one right here, voltage divider, VI divided over these two, suppose that VI is 10, R1 is 100, and the maximum power rating for each resistor is 250 milliwatts. What resistance for R2 gives the highest current flow through R2 when the output's disconnected? So there's no way that current can go into V out. All the current that goes through there goes through there. What happens then if we connect a non-infinite load resistor RL? I guess that would be a finite or a finite load resistor RL. So the best way for you to learn, if you have some idea of how you're going to be doing this question, the best idea for you to learn is to pause the video and give this a shot. Try and work through it on your own. If you're completely lost and you've given it a shot, then by all means look at the solution first and then try and come up with a different version on your own. If you think you know what to do, then start and only look at the video when you're done or you got stuck to see how you did. Okay, looking at the solution now. With the output disconnected, current through each one's the same. Power dissipated in R1 would be I squared R1. So since the current everywhere is the same, it's good to work with the current. We need this to be less than 0.25 watts. Solving for the R2 that gives this power for R1, we come up with a condition on R2. R2 has to be at least as big as R1, at least as big as 100 ohms. So then we can go on from there and calculate how much power would be dissipated in R2. It's a little bit obvious given that it's the same resistance as R1, but let's imagine in a more general case, suppose we set R2 to this limit for maximum current, then how much power gets dissipated in R2? Well, P2 would be I squared R2. Substituting in, we can simplify that the power in resistor 2 is related to the power in resistor 1 through the ratio of the resistances. So the bigger resistor is going to get a bigger share of the power. That makes sense because the power is I squared times the resistance and the current through each one is the same. Now, why was it that the power in each resistor was the same? Did it have to be the same? Is this like a property of maximum current through this whenever you've got a power limit? Well, no. You can see that it had to do with the specific power limit that we set. If the power limit is multiplied by 4, then it's like we're dividing this first term in half. So instead of being 200 to give us 200 minus 100 is 100, we would have 100 minus 100 is 0. So that means if the power limit for the resistors was doubled, we would have found that we don't actually need an R2. R2 can just be 0, and still we're only barely getting the power dissipated through R1 to be up at that limit. All right, so going on to the second part of the question, it says, what happens if you add a load resistor? Well, coming back to the case where R1 and R2 had to be equal for the exact numbers that the question was using, any load resistor is going to lower the resistance on the second branch of the circuit. So this is going to increase the total current going through, and since R1 was already at its limit, that's going to push it over the power limit. What happens when you exceed the power limit of a resistor? When you exceed the power limit of the resistor, it depends on what kind of a resistor it is. Certain resistors will fail to open, certain resistors will fail to closed, and there's some randomness involved too. What do these numbers mean? Failing to open means that when the resistor burns out, it becomes, it's not a conduction path anymore. It's like if the resistance goes way up, so it stops the current flowing in the circuit. That's probably bad, but it's not usually nearly as bad as failing to close. This is when the resistor burns out and becomes a short circuit, allowing a lot of current to go through, probably breaking other things elsewhere in the circuit. Either way, though, there's a lot of heating up that happens before resistors fail, so this could cause fires and other nasty things. Basically, try not to exceed the power limit in your resistors. On to exercise 1.6. Now we're given the task to design a voltage divider that will divide a 10-volt source by a factor of 5, and also has less than a 5% droop when a 100 ohm resistive load is connected to the output. Think about what that means. So basically, we've got two constraints here. We need it to divide the 10-volt source by a factor of 5, which means that we need the ratio of these two resistors to be 1 to 4, so that the ratio of this to the sum is 1 to 5. And the other part is we need that when we connect the harder part of this is when we connect to figure out the size of the resistors, so that when we connect a 100 ohm resistor here, the output doesn't drop too much. Okay, give it a shot. Moving on to the solution. Setting up both of those things as an equation, the ratio of the output to the input from the voltage divider, and then assuming a load resistor as well, RL, leaving that as a variable for now, we can write out what the output to input is. Now we need that to be no more than a 5% droop. Solving for the load resistor, or rather the input that gives us a 5% droop, says that the ratio is 0.19. If we put in RL is 100 ohm, then you find that R1 and R2 are 26.3 and 6.6 ohms. Now a great concept question to do from here is to think about how the size of the resistors mattered. So yeah, we've got these specific numbers, but what does that mean? If you use higher resistors, then what does that do to the output? Does it mean that there's more droop or less droop? If there's less droop, then for whatever resistor direction, then what's the trade-off for that? Because wouldn't you want to just make a voltage divider that has the lowest amount of droop possible? Well, as usual, there's a design trade-off. So see if you can solve that on your own. And once you're done, we'll pick it up right here. So how do the droop specifications affect the results? Let's just explore this first. Suppose we wanted less than 1% droop. So now we change the droop to 0.99. Solving again, we find that we need even smaller resistors. Okay, that's interesting. So in the general case, we can model the droop D using the same sort of strategy, leading us to a droop that depends on the relative values of the input resistances. Basically, to get very low droop, you need very low resistances for your voltage divider. That kind of makes sense. If the output resistance is going to be lower than this resistance, it's going to affect the circuit more when you put it in parallel there. So you want the output resistor to be reasonably high compared to this, or sorry, the input resistor of your load to be very high compared to the output impedance of your voltage divider, the output impedance here. So in other words, you want the resistor here to be very large compared to these resistors. But the trade-off to that is that your voltage divider is going to be draining more power if it's got lower resistors to do the same thing. So it's not necessarily the best circuit to use as a steady supply. We're going to see some more advanced circuits later on that get around this problem. Exercise 1.7. For the circuit diagram shown in figure 1.14, repeated here for your convenience, write down a matrix equation of 5 linearly independent equations for the 5 currents through the resistors. In other words, some kind of set of equations that you could solve for the currents and write them in a matrix form, because everybody wishes they remembered how to do these things quite well from first year linear algebra. So if you haven't used matrices to solve systems of linear equations in a while, this could be a good review of how to do that. Okay, give it a shot. Welcome back. Here we go. We've got the current directions. You can label these however you like. Assuming that we label them with the same resistor that they're in the branch with, we can get these loop equations and these node equations, as usual, assigning the positive direction to help make sure that you go around everything correctly, labeling the voltage rises and drops. If you cast this into matrix form, you should have something that looks kind of like this. That's very convenient if you wanted to substitute it into a computer algebra system to solve, so something like MATLAB. If you're going to be solving it by hand, it's probably not the best idea to write these in matrix form, because the matrices end up being kind of sparse, so there's a lot of extra zeros that you'd be writing, and the numbers you're dealing with are probably complicated, non-nice integer values. So doing the math by hand is not as nice as it was with the matrices you were solving in first year. So most of the time for solving circuits, if you're going to be doing it by hand, it's better to just work with the equations, solve one equation for one of the currents in terms of the other one, substitute that into all the others, solve the next one for one of the currents in terms of one of the remaining ones, sub that into the remaining equations, and proceed until you can get a number value for one of the currents and then back substitute. Section 1.5, Equivalent Circuits and Current Sources. Thevenin equivalent circuit theorem says that the output of any network of resistors and voltage sources is equivalent to the output of a perfect voltage source, called the Thevenin voltage, and a single resistor in series with it, the Thevenin resistance. What that means is you can replace this sort of a network with this sort of a network, and both the networks will have the same effect on any kind of output circuit that you would put over here. So if you're just looking into this and you don't actually know what's inside this, like it's a black box, you've got one terminal, you've got another terminal, you hook up an output there, the equivalent circuit will produce the exact same output for any kind of circuit that you put on the output side of it as the original one would. So in terms of analyzing it, it's much more convenient if you're going to say, like, what would the effect of my circuit be on this output? What would it be on this output? What would it be on this output? If you're going to do that several times, it's really convenient for you to go and find the Thevenin equivalent of your network before you do that, because it makes the analysis a lot simpler. All right, how do you do that? Well, you figure out what voltage you would have if it was open circuit, and that should be the same for this one and this one. And you figure out what current you would get if it was short circuited. That should be the same for this one and this one. A shortcut to the short circuit current, you can look at this and see, okay, well, the short circuit current is going to tell us the Thevenin resistance. Thevenin resistance is going to be equal to the voltage divided by the current by Ohm's law. And a shortcut to find this resistance, which is quite useful, is to replace all the voltage sources with equivalent, with what they look like from a resistor perspective. And the voltage source is replaced with a short circuit. Current sources, if we had any, would be replaced with an open circuit. So then we can just add up all the resistors without having to worry about these sources being in the way. So these two are in series, and then that combination's in, or sorry, correction, these two are in parallel. After this is gone, that combination is in series with R3 and R4. Combine those, and then that combination is in parallel with R7. That new combination is in series with R5 and R6, and we've got our Thevenin equivalent resistance. Then we can find the voltage source by taking loop equations. Often it's useful to use the superposition theorem, which you may remember from second year, to do this as well, which is to just turn on one voltage source at a time and figure out what that would produce on the output, then add them up, because voltage is going to add linearly due to all the linear elements and linear equations that we're writing here. Okay, there's also a Norton equivalent. Norton equivalent is the same idea as Thevenin equivalent, except instead of a voltage source in series with a resistor, you have a current source in parallel with a resistor. It turns out that once you find the Thevenin equivalent, you can get the Norton components by saying the resistance is the same and using Ohm's law on the voltage and resistance to get the current. Section 1.6, understanding the equipment multimeter. This is an example of one of the sections in the book that we're not going to typically do. The book has a bunch of sections titled Understanding the Equipment, Application, like section 1.7, and a number of advanced sections. Generally, we're going to be skipping that in the lectures, but it's a great chance for, or rather, it doesn't mean that you shouldn't have a look at those if it's something that you're interested in, and some of them will be useful for helping with the labs. So the reason that we're skipping them is just for the sake of time. The book has a lot more material in it than we could really cover in a one semester course. Even as it is, we have to go pretty fast through a lot of topics. So there's no way that we could get them all done and do all the application sections without blowing a lot of your fuses, so to speak. Okay, in this chapter though, we are going to take a section to go through them just to show you what you're missing for some of those other chapters when we don't really cover them in detail. Multimeter. Older analog multimeters used to perform a current measurement directly when in current mode, and then indirectly measuring voltage via that current mode through a large resistor. Modern digital multimeters actually perform a voltage measurement. So either way, the meter needs to have some kind of a pretty large resistance when you're measuring voltage, or it's going to mess up the circuit that it's trying to measure. Another important thing to know is that the multimeter, when measuring resistance, does it by trying to send a current through the leads and measure the voltage that's necessary to do so, which means that if the resistor is attached to an active circuit while you're trying to measure it, you're going to get pretty strange results for the resistance. Imagine you try and force a current into the circuit, but the circuit is forcing the voltage to be some specific amount. The multimeter is going to measure the voltage different than the voltage just from the resistor itself. So that'll be a little bit odd. Section 1.7, application 4-lead circuits for extremely sensitive measurements. What this is talking about is if you've got a really small resistance that you're trying to measure, say right here, and you hook up your multimeter, that's this, you've got a voltage measurement, but it's got some internal resistance, then the problem is when you connect it, there's a contact resistance that shows up on both parts where you have to make connection to this small resistance. Just because you've got probes in the multimeter and you have to connect them somehow. Whenever you connect them, there's a couple of ohms, maybe half an ohm to 2 or 3 ohms in contact resistance. And if that's significant compared to the resistance you're trying to measure, you're not going to be able to measure it right. The contact resistance is very sensitive to what the contact area is between the two terminals. You can try this yourself by trying to connect one probe to another one on a really sensitive resistance reading, really sensitive resistance range, and see that it's quite tricky to do that with consistent results. So basically, this is not a good way to measure the resistance if it's a really small resistance compared to contact resistance. A better way to get around this is with what's called a 4-point probe measurement. So here's what you do. You make 4 contacts to the resistance that you're trying to measure. So one contact over here through some other resistance, another contact over here through another resistance, one contact on one side of it and another contact on the other side. And yes, the contact resistance is there as well, except that now, because you're forcing a current to go through with this current supply down here, the voltage drop that you're measuring is not because you don't have to put this multimeter in resistance mode like we did up here and force a current to go through. Down here, you just put it in voltage mode, where the voltage drop is really just happening because of the current going through this one. There's no current going up through here, basically, compared to the current that's going through here. And so the 4-point probe makes a much more sensitive measurement. We have a setup to do this over in the tandem accelerator building. So if you go over there, if you've worked in the summer, then you can ask Sharam where the 4-point probe sensor is, and it's set up so that you measure the voltage and you measure the current and use that to figure out what the resistance is, using an equation that you can go and derive with all the math that you know right now. Section 1.8, the physics and chemistry of batteries. Different atoms have different work functions. Work function is the energy that's needed to remove that outer electron. For larger Z atoms, generally larger Z atoms are going to have a lower work function, meaning that it's easier to remove that outer electron, but there's all kinds of exceptions, so you're going to want to look these up in a table before you make any calculations with them. Iron's work function is a little bit lower than nickel's work function. That means that it is easier to remove an electron from iron than it is to remove it from nickel. And it also means that if you take an electron from iron and you move it over to nickel, then some energy is released. And that's actually what happens on its own. If you were to connect a block of iron to a block of nickel, electrons are going to flow from iron to nickel until the charge that builds up stops the electron flow. Exercise 1.8. Write down but don't solve all the independent node equations and independent loop equations you'd need to solve for the currents and voltages of the circuit shown in 116 using Kirchhoffs laws. So that's this circuit right here. There's the directions we're going to use. Give it a shot. Welcome back. All right, so for the loops, you can get these equations, and for the nodes, you get these equations. Notice that this is if you've decided to write I7 and I6 as their own ones. You could have just used I1 and not really had another equation there. How many different nodes do we have in this circuit? We've got 1, 2, 3. These two are really connected by a wire, so it's like it's one node. Now, this means that we can only have 2 different node equations, unless you want to consider the currents like this one as a separate variable name than this. Then I guess you'd have another node equation for each junction in between. That's a matter of debate though. So in terms of if we don't do that, if we were to just write this all as I1 off the bat and then assign a different current to each branch, we would only have 1, 2 different node equations, or the way we wrote them here, 1, 2. Solve for the current in each resistor shown in figure 124 using any method you choose. Both voltage sources have the same voltage output. So this is one where you don't actually know the numbers. You've got to solve for the currents in terms of these voltages and resistances. Okay, solution. Imagining using Kirchhoffs laws, we can have 2 loops and then 1 node equation, write out the equations, and we're done. Solve away. Exercise 110, prove the statement that an imperfect voltage source, which is modeled as a perfect voltage source in series with an internal resistance, is equivalent to a perfect current source in parallel with an internal resistance of the same value. To do this, solve for the current through a load resistance connected across the output in each case and show that it's the same for both sources when I of the perfect current source equals V of the perfect voltage source divided by Ri. In other words, they're asking you to prove the Thevenin and Norton equivalence theorem relations that we had earlier. All right, so let's figure out the current for the voltage source and the current through the load for the current source. And if the Thevenin current is the Thevenin voltage over the resistance internal, then we find that the resistance internal is just the Thevenin resistance.